Imagine a system that handles millions of dollars in Bitcoin. It seems stable. It has rules, multi-signers, and protocols. Yet, a tiny misstep, a desynchronized signer, a subtle interface bug, and suddenly hundreds of transactions stall, fees spike, or funds are at risk. All perfectly valid, yet unsafe in practice. This is the world where infrastructure and governance must meet head-on. Today, we explore foundations before the code, designing systems so unsafe states simply cannot exist, whether in Bitcoin, AI, or other autonomous systems. Conceptual framing. Conventional governance often fails because it is declarative and reactive. Policies exist on paper, but by the time enforcement acts, damage may already occur. High capability, persistent systems need embedded governance built into the runtime layer itself. This is what we call capability-tiered governance, aligning oversight with the system's autonomy, persistence, and economic activity. Analogy. Quote, "It's like designing a bridge so it cannot collapse. You don't inspect after the fact. The unsafe state is structurally impossible from the start." End quote. Core message. Prevention is greater than detection. Enforcement and constraints must be part of the system's architecture, not an afterthought. 3. Lessons from Bitcoin PSBT consolidation. PSBT equals partially signed Bitcoin transactions, often used in multi-sig setups for treasuries. At scale, small operational misalignments create non-cryptographic failure modes. 1. Signer desynchronization leads to stalled operations and confusion. 2. Authority creep leads to accidental centralization or unilateral power. 3. Custody diffusion leads to unclear responsibility for funds. 4. Audit breakdown leads to errors go undetected, compounding risk. These aren't theoretical. They happen in live treasuries and wallets. Takeaway. Deterministic invariants are necessary. Rules that prevent unsafe states regardless of human error or network volatility. 4. Invariant technical memo teaser. We're formalizing PSBT consolidation invariants in a technical memo. Purpose. Define what must never break operationally and make unsafe states unrepresentable. Collaboration with formal verification teams explores methods like differential fuzzing to stress test these invariants. Why this matters. It creates a predictable, auditable, and resilient foundation for Bitcoin infrastructure and governance. 5. Bridging to AI. The same principle applies to AI governance. High capability systems must have embedded control layers, not just policies. Risk grows with autonomy, persistence, and economic agency. Think of deterministic invariance as a shared philosophy across domains. Quote, whether Bitcoin or AI, it's about building systems that cannot fail silently, that encode safety at the structural level. End quote. 6. Broader strategic takeaways. Deterministic infrastructure-aligned governance reduces operational risk, ensures transparency and verifiability, supports alignment with national and international standards, strengthens sovereignty over critical infrastructure. The work isn't about controlling systems. It's about designing resilience, preempting failure at scale, and creating a platform for safe growth. 7. Closing. Reflective close. Quote, the systems we design today, Bitcoin infrastructure, AI frameworks, complex digital operations define what is safe and what is possible tomorrow. By building foundations before the code, we choose stability over fragility, foresight over reactive panic. End quote. Call to action. Quote, in future episodes, we'll dive deeper into operational invariance, security proofs, and deterministic governance frameworks. For those curious, a technical memo is coming that formalizes these ideas into actionable rules. End quote. Sign off. I'm Federico Blanco Sanchez Llanos, and this is Baby Blue Viper, exploring infrastructure, governance, and the hidden threads shaping our digital future. End quote.